During the 1960s, while NASA was engineering the hardware to put humans on the moon, a parallel race was happening in the exact opposite direction. The goal was to build permanent human colonies on the ocean floor. Early missions, like Jacques Cousteau's Conshelf and the U.S. Navy SEALAB, were driven by intense geopolitical and industrial pressure. The French petrochemical industry wanted to drill deeper for offshore oil, while the American military wanted an underwater tactical advantage. But living at those depths meant operating in an incredibly hostile environment. Aquanauts endured freezing temperatures that sapped their body heat, and the heavy pressure required them to breathe a dense, helium-heavy gas mixture. Even with specialized suits, the cold was relentless, and the physiological strain was immense. The breaking point came in 1969 with SEALAB 3. The massive multi-million-dollar habitat began leaking helium almost immediately after being lowered into the Pacific.
While trying to repair it, Aquanaut Barry Cannon dies from carbon dioxide poisoning after his breathing apparatus failed. That human cost, combined with the development of cheaper robotic submersibles, shifted the focus away from human habitation. For the next 50 years, the dream of living on the ocean floor was largely abandoned. Those early habitats were left to rust and encrust with coral. But recently, marine technology companies like Deep and the Proteus Ocean Group announced they are building new, permanent human stations under the sea, aiming to have people living there by 2027. Which raises a massive question. If the ocean floor remains one of the deadliest environments on the planet, and history has already proved how difficult these missions are to sustain, why are we spending billions to go back? Currently, marine scientists rely on brief dives from the surface, dropping down for a few hours before their air runs out or they need to decompress. But marine ecosystems are changing so rapidly that surface incursions aren't enough. To accurately study the water, we need researchers living on site, observing and experimenting 24/7. While the 1960s were defined by industrial extraction, these new ventures are pitching a different mission. Companies like Deep are betting that the value lies in understanding the blue economy, from carbon capture to pharmaceutical research, which requires staying down long enough to actually see how the ecosystem works. To survive down there today, engineers had to scrap the original 1960s blueprints. Instead of stuffing researchers into single, cramped steel cylinders, the new architecture functions more like a scalable college campus. Deep's Sentinel system is entirely modular. Individual living suites and research labs link together, expanding the base exactly as needed. The assembled system can then be safely towed, lowered, and locked into position at depths of 200 meters. Off the coast of Curacao, the Proteus Ocean Group is planning a similar base, but with a heavy focus on daily quality of life. Their facility includes an onboard video production studio to live stream research and an underwater greenhouse to cultivate fresh food. By incorporating natural light simulation, communal dining areas, and private suites, these stations are designed to mitigate the isolation that plagued early aquanauts. The goal is to move past the survival mindset of a submarine toward the functionality of a land-based research lab. But an underwater campus still requires massive logistical support. If a base wants to sever its umbilical cord to the surface, it has to generate its own continuous electricity and fresh drinking water entirely from the ocean around it. Future concepts like Shimizu's Ocean Spiral will use ocean thermal energy conversion, or OTEC. OTEC exploits the massive temperature gap between sun-heated surface water and freezing deep-sea currents. Running both streams through a heat engine spins a central turbine, producing continuous electricity. To solve the drinking water problem, they plan to use the ocean's own crushing weight. The extreme pressure at the seafloor pushes salt water through specialized reverse osmosis filter membranes, removing impurities and creating a steady supply of fresh water. By mastering these closed-loop systems, future habitats won't need to drain resources from the mainland. The ocean provides exactly what is required to sustain them. While massive city-sized structures are still conceptual, the immediate goal for 2027 is highly specific, putting teams of scientists underwater for stretches of up to 28 days at a time. They will operate primarily in the epipelagic, or sunlight zone. This is the top layer of the ocean where light still penetrates, and it happens to be where 90% of all marine life lives. This hardware is currently in production.
Deep is actively manufacturing habitat modules and has already converted an old flooded quarry into a 600-meter-long underwater testing and training facility. The steel is already being cut, and the training facilities are open. We aren't looking at artist renderings. We're looking at a manufacturing schedule. The long-term trajectory goes far beyond small outposts. By mid-century, developers are mapping out underwater cities capable of housing up to 5,000 people. We currently spend billions of dollars and countless engineering hours trying to figure out how to colonize the dead dirt of Mars. Yet the solutions to our most urgent generational challenges, like mitigating climate change, discovering novel pharmaceuticals, and securing our food supply, are locked within the ocean right here on Earth. Going back to the deep isn't about repeating the 1960s oil rush. It's an admission that we can't protect an ecosystem we don't inhabit. If 2027 is the starting line, the next decade will be defined by whether we can finally live alongside the biology we've spent the last century merely skimming over.